Because the not unfortunate, it's good for me because I love maths and stats, is that you can't sometimes remove the content of the stats from just the R coding itself with machine learning. You have to actually know what the methods are, when to use them, and I thought the best way to teach you guys this today would be to actually show you some slides about this, and then next week we're going to be working through together, if you're still interested next week, in how to see how well models work in practice. So as Jen said, I'm a third year PhD student and I work in, before, like last year I would have said I work in statistics, but I found it didn't really work that well at parties, so I changed it up to machine learning. Because you'll see, machine learning is the biggest buzzword of all time, right behind artificial intelligence. These slides will be, they're already actually, if you type in this link, they're already online right there, and then the repo will be published not privately, publicly, right after this, so you can have a look at all the slides and how I made them. So that was my little welcome. Okay, so today, as I said, this is just a small taster into the field that is machine learning. Of course, I have 2 hours. I haven't quite timed this. I always wing my talks, never ever time them. We're covering some supervised learning machine learning techniques, which I'll cover what that word means in a second. But of course, I can't go into too much detail into all the techniques or cover all of them. And then next week we'll cover model performance assessment. But if something in this talk piques your interest, this book here, I've got a link to it as well. It's you can get a hard copy if you like, but it's a free PDF online. It's by some amazing people. James Witten, who I met in person, and I was such a fangirl in front of her. Trevor Hasty and Rob Tipsharani. They made this really good textbook, which is very introductory. If you haven't done stats before, it doesn't assume too much maths or or like statistics knowledge. You just kind of work through it, and they have R examples as you go through as well. And then you can look at the other book called The Elements of Statistical Learning, if you want to go to another higher level above that as well. And so, as I said, you won't be this is going to be a very broad and general talk, and I like to make it quite lighthearted, so I do like to put a lot of memes throughout my talks. I do this for my lectures as well with first years. Even if I was a third year lecturer, I also would give them memes as well. I think making talks fun is a really good way to boost morale. So, as we start, what is machine learning? So I think the biggest buzzword, I use it to my own advantage, but I also hate it at the same time, is machine learning. And all machine learning is concerned with finding functions, so some function of your data that best predicts outputs or responses given data inputs. We call these predictors. So if you're reading textbooks, you might see the word predictors used for data, and you might see responses used for the output. And so all we're trying to do is, given some input, find some function that best describes the data. And depending on what data you have, you're going to pick a different function to best model your data. If you've done some mathematics before, in the end, machine learning problems are simply optimization problems. So if you ever done maths, it's really, you're going to be using stats and optimization to help you solve these. But we're going to be using R a lot to just help us solve through all the nitty-gritty mathematics, all behind the scenes, and we don't have to touch any of those horrific equations ourselves. So why do machine learning in R? So if you've heard of all the languages out there, R and also Python are very much used to do machine learning problems. Python's seen a bit of a jump in the recent year, but both, and we can see that it's also quite a lot of people using both R and Python. And both of these languages can work really well together to have really nice workflows for machine learning problems. So the good thing about doing machine learning in R is that a lot of people have used R to solve machine learning problems. So a lot of libraries and packages there for you already to use. And you don't have to worry about coding up algorithms yourself. Also, there are some libraries in Python as well if you're so inclined. But of course, this is RLadies, not Python ladies, so I won't be spruiking Python too much. But I'm not going to bag Python. For my current PhD project, I'm actually double coding my last project in Python as well, just to see how it all works out. Python is supposed supposedly supposed to be faster in some respects if you use the functions correctly, but just showing that there are a lot of tools out there for you at your disposal, and R is a pretty good one to start if you're doing machine learning. So overall, there are pretty much two different types of machine learning, and so the one we're going to be touching on today is the first one, which is called supervised learning. And it's called supervised because you have knowledge of, for your data set, what the actual responses are. And your goal is to train a model or to use these responses to help the computer figure out the function that best describes your data. And then when you get a new data point, you can use that model you trained to predict a new data point. So in this case, for example, that corresponds to the first picture where you've got some data points with two variables. This one belongs to one class, this one belongs to another one, and you're trying to find the best way to separate the two data points. So if a new data point came along, you could easily figure out if it belongs to the first class or the second class. Unsupervised learning is when you have no output of the class or response it belongs to. All you have is just unlabeled data, and then your goal is to determine the patterns or groupings they form into. So here, in this case, all these data points come with open circles, so you have no idea what response they have, and your job is to build the circles around them and to figure out what classes they should belong to. So there are two completely different problems, many different types of methods to solve the two of them, and the one people learn first mostly is supervised learning. So that's what we're going to be focusing on today. If you want to know more about unsupervised learning, I would recommend looking at their textbook I said before, or they have some really good data camp tutorials as well. If you're so inclined, I think it's actually a really good resource. It helped me build my very first Shiny app a couple weeks ago. So they have a really good machine learning course on there as well. So within supervised learning, there's two main types of problems. And so the first type of problem is called a regression problem, and then later on we're going to be touching on something called classification. So here's the first component, regression, and I hope I'm not boring too many people in the room. I know many people have seen linear regression before, but I did notice from the very first RLadies talk, and I looked at the bar plot of how people expert levels were. We had a lot of beginners in the RLadies Sydney cohort, so I thought I'd start from the beginning, and hopefully maybe you might find something a little bit interesting if you've seen regression before. So we have a very simple prediction problem. So all these data sets are on my GitHub, and so later when I get home tonight, I will make it public, and you can go home and play with these data sets yourself as well. So this data set income came from that textbook I showed before, and it's a simulated data set. So it looks at the relationship between education years for some individuals and their income in thousands. And so here I'm just looking at the first couple of rows. So we've got two columns, education, income, and we have the first 6 observations being shown. First thing we're going to look at is asking ourselves, what is the shape of the relationship? And we're going to ask ourselves, can we build a function to predict the value of a new data point? So what I like to do with any machine learning problem, the first step is to kind of look at the data you have. Sometimes people I had that problem when I was my PhD. I was very excited to just put all my honours knowledge to work and start modelling things. And I wouldn't actually even look at the data, I'd just go model. So the first thing I like to do is actually look at the data. So the nice thing you can do is plot it. So when I look at the plot of education versus income, the first thing I notice is that seems to be a relatively linear fit between education and income. There's a bit of a dip here, but you can, first thing you might think of is to fit a straight line relationship between income and education. And I also notice that my inputs and my outputs are both continuous data. So what I'm trying to do is when I want to predict a new data point, if I give it a new education value, I want to predict the value of their income. So that's a continuous data point. And that's what regression is. So when we're using regression, you're trying to train your model to predict a new continuous outcome. And so you might have guessed that linear regression comes to the rescue for this. And I think this is one thing that people often forget, is that because machine learning in its essence is predicting an output from an input, that linear regression is a machine learning method. It's not all about, you might have heard neural networks or deep learning or some very fancy classifiers out there. Linear regression is a machine learning method, and I think sometimes people tend to go for more complicated solutions rather than the simpler ones because it sounds a bit more fancy, but linear regression a lot of the time is actually the most widely used thing in the world. So what we're going to do is going to use a linear function just to describe our data and predict a new data point. And the question is, the million-dollar question in all machine learning problems is, what is the optimal function? Or in this case, what is the optimal line? So there are many different lines that could fit between all those data points. And so don't have to worry about doing this maths by hand every time you do a machine learning method. But just to show you is that one way to do this is to find the slope and intercept that minimize the sum of the squared residual data points. So if you're mathematically inclined, if I have my actual data point here, and I have the data point I estimate from the line itself, the residual sum of squares is just the sum of that squared distance. Now this makes, when I was in first year, I was like, what is this? And so I made a Shiny app to show you what this visualizes realistically. So hopefully this app works. I'm in full screen. How do I exit? Does anyone know how to? I'm stuck in my. Oh no! How do I escape full screen? This is not good. This is not part of the show.
What are we trying to do?
I'm trying to exit full screen. I try to press escape.
Are you trying to get to
Yeah,
the browser?
yeah.
Or to...
Maybe I'll try. Sorry. Try making another little window. Type. Oh, it's very slow. How do I do that? Oh, there we go. So I tested it this morning and it worked. So hopefully the connection is stronger. Spent a very long time making the shiny. I learned all the stuff from Emmy's course. Is it the internet? If I hotspot my phone, good. Let me try. Hotspot is on. Ah, there we go. So here we have this. You might find it scary. You might find it beautiful. I love mathematics, so I find it beautiful. It's a beautiful equation. And so what we're going to do is that we've got this is the same data set as before. And what we're going to do is we're going to slide. We're going to change the intercept and the slope, and we're going to see how this sum, called the residual sum of squares, changes. So the residual sum of squares is the squared distance between our line and the point. So it's literally these squares here. And what I've done is I've tried the starting values are actually the closest I could get to the actual optimal values that I got from running the algorithm in R. And so this is what the smallest, when you adjust the line, this is the position where you get the smallest sum of all those, the area of those squares. To show you how it really can change, the intercept is where the line crosses this axis here. If you push it all the way up to minus 32, for example, your residual sum of squares more than doubles, and we see we're getting a lot bigger squares, so that's obviously not the optimal line. Maybe go in the other direction. Here we're really missing the mark on quite a lot of those points. And you can also play around with the slope at the same time as well. It's not a very good line at all, that one. And so luckily we don't have to make shiny apps every time and figure out for ourselves what is the best line. So I even forgot. Oh, here's 9. We're getting pretty close again. So that's what it does. So what R is doing is it's trying to find that line that minimizes the sum of those squares. And so this app is online, so you can also play around with this at home as well if you like playing with shiny apps. And mathematically, this is just an optimization problem to find the values of beta naught and beta 1. So beta naught is your intercept, beta 1 is your slope that minimize the line. So the line is described by y equals the gradient x plus b, y equals mx plus b. We're trying to find m and b, or in statistics world we call it b naught and b1, to best describe our data. So I've lost my slides now, so I need to go back. Now you want to keep it not full screen, just in case. Okay. So luckily for us, R performs optimization process when we call the LM function. So quite nice. I like the thing about R is everything is called what you think it is. And I just thought I'd chuck in a little plug to my website where I used ggAnimate to also describe fitting a straight line without any calculus whatsoever. So if you don't like calculus, there's also another way we teach first years at my university how to fit a regression line as well, and you end up getting the same line but through a completely different derivation. So that's one thing I love about stats, you can get to the same thing through different methods. So if you want to look at that, the little link is there. So now here is where I show you how to actually use R to solve these problems. So what I'm going to do is I'm going to call the linear model function. So what do we have to put into linear model function? So first we have to tell it what data we're referring to. So I called my data set data. That's what I do all the time, just data, not very descriptive. Then I'm going to tell the linear model function what variables I would like to regress and what order it should go in. So R expects the relationship in the form of your response against your predictors. And so if you did it the other way around, it would be thinking you're trying to predict education from income, but we really want R to say, hey, if I give you some education values, can you tell me what the income will be? So that's sometimes things in R don't matter what order you put them in, but in this case, order does matter. And so when you run that, you get an output. What is a lot of stuff you don't have to worry about what it means. The most important things you have to know is you have to be able to read off what the values for the intercept and the slope of your line are. So luckily, our intercept is called intercept. So it's telling you that the intercept, the line cuts the y-axis at minus 39.4463, and it has a slope of 5.5995. So that straight line that best describes our data is income. Your income is equal to minus 39.4463 plus 5.5995 times how many years of education you have. R also gives you some other information. You can have a look at the residuals is the distance between the line and your actual data point. So you can see that the maximum distance between your line and the data point is 10.1. The minimum is in the opposite direction is minus 13.046. Not looking too bad. Obviously, you don't want your residuals to be too big. That means your data's not fitting. The line's not fitting your data that well. And I find that all this output here is more important for when you have more than one predictor going in, but we're not touching that today, so don't worry. That's a whole third year subject in itself. So now you fit this line, so you actually want to be able to do it's cool to describe the line, but you want to be able to do something with it. And so what I'm going to do is we can aptly use the predict function. So predict is very versatile. You'll see it popping through in every method I use today. So predict will adapt itself to what model you put in. So I've called my linear model fit as also, you'll see that through I call it data equals data. My model is equal to fit. It's not very descriptive. And so here my model is, the line I've described is called fit. And here I've got some new data points. So suppose I've got two individuals, one has 15 years of education and the other one has 18 years of education. You have to be careful about what form R expects your data to be in. And so for a linear model, you would expect it to be in terms of a data frame. Another one that comes up a bit is a matrix. So you might, if you haven't seen a matrix before, a matrix is very similar to a data frame, but has all the same types of variables within the data frame itself. So sometimes it expects a matrix, sometimes it expects a data frame. It's good to look up the help descriptions to figure out which one you need. In the case of this model, it expects a data frame. And so what I do is, to use the predict function, I put in the model I trained, and then I tell it, here's my new data, and then it spits out the predicted values. So it says, if you've got 15 years of education, you can expect to make $44.54 thousand. And if you've got 18 years of education, you can expect to make $61.344 thousand. And so we can, once you fit the model in R, you could get pen and paper and work that out yourself, but it's actually really nice to do it all via R as well. So another type of data you will see is binary outcomes. So the outcome we saw before, so we had education against income. Income was a continuous response. Another outcome that's commonly seen is a binary outcome, where it's just a 0-1 response. So yes or no, anything can be dichotomized into two classes. So here we consider data set spiders, which is actually from a paper in Japan, where a study looked at the relationship between grain sizes of sand in beaches in Japan and spider presence. So if a spider was present at that beach, they put a 1, and if it wasn't, they put a 0. So here you can play around with the spiders. I've cleaned up the data set a bit, and it's on the GitHub repo. And here, just looking at the first couple lines, here we have the first grain size is, I think it's in millimeters, so 0.245 millimeters. And for that grain size at the beach, there was no spiders. Second grain size, there was no more spiders as well, and then we got to 0.285, and there was a spider. And so what you might think is can you use the linear model function to predict the class for a new data point? So can you use LM to take in the input of grain size and predict whether you're going to get a spider or not a spider? Plotted here, we have the relationship between grain size and spiders. So the general trend, it seems that is for smaller grain size, you don't seem to have spiders. And then towards the top, if you get to bigger grain sizes, you tend to see some spiders a bit more, but it's not completely separated. You have some spiders appearing for some lower grain sizes as well. So this is when we have to bring in some statistics, is that to model binary data, so a 0-1 output, we have to link our predictors to our response using what we call a link function. So aptly named, linking link function. And so what we do is, instead of predicting the outcome directly, we are going to predict the probability of being class 1. That's just by convention. So that they could have had convention of being class 0, but they decided to make the convention class 1. And what we're going to do is we still have some predictors. So we still have that linear relationship. We have beta 0 plus beta 1x. So x will be the grain size in this case. We're trying to find an intercept and a slope. But in this case, we're going to take the output we get from that and then transform it to a 0-1 value. And that 0-1 value is the probability of being class 1. There are many different ways, if you are familiar with functions, that you can transform things to a 0-1 space. So don't worry, you don't have to know these equations at all when using R. You just put in the function you want and does it for you. But just so you know, the logistic link is called logit in R. Takes beta 0 plus beta 1x and gives you an output in 0-1 by doing 1 over 1 plus the exponential of that combination on predictors. And then another one is called the probit link, which is, if you're familiar with normal distribution, is a probability of beta 0 plus, whoop, wasn't supposed to do that, beta 0 plus beta 1x being less than in your standard normal curve. All it does, so there's not much difference between using a logit link or a probit link. If you look here, this is if you've got your linear combination of beta 0 plus beta 1x, there's some number that could be any real number, so it can be all the way from infinity, minus infinity to positive infinity, and it maps it. So you see here is 0, here is 1, and it maps it to somewhere in between 0 and 1. And you can see here, no matter the difference between the two links is very subtle. So you can, most of the time, you can just pick one or the other. It only really matters a lot of time when you're doing mathematical working out, and sometimes one can be easy to use and the other one mathematically, but we don't have to worry about that at all. So how do you fit, and what we actually call this is called a GLM. So it's called a generalized linear model. So you just add a G on front, because with a generalized linear model, you can be a lot more general with how you link your linear combination predictors to any output that you want. So in R, we use the GLM function, so it's aptly named as well, and it's a very similar setup to the LM function. So the first two components are the same. So the first component of a GLM, you tell it what data set you're referring to, so data equals data. The second component is what variables you want to regress. So in this case, I want to find out the relationship between spiders, that's my response, yes, because spiders or not spiders, and the grain size. But there's one more argument we have to pass through, which is the link function, that thing I was talking about before. So do you want to use the probit function, or do you want to use the logit function? And there's many more, so just showing another case, you could do C log log. I never used that before in my life, but that also exists out there as well. There's many different types. They all give you very similar answers as well. So what we have here is that we have the family equals binomial. The binomial part tells us it's a 0-1 output, and the link tells us how we want to map to the 0-1 output. So the reason why we have that family component is because the GLM can also predict many other response types. So if your response was counts, so full number counts, you can also model that using a different family. So we're not going to touch on any other GLMs today, besides from the binary output. And so you only have to use the binomial family for that. If you do stats, you might know where the binomial comes from, but if you don't do statistics and you don't want to know, you don't have to worry about where it comes from, just remember it's called binomial. So for this example, I'm going to go with the most commonly used one. So a lot of times when you're talking about modeling 0-1 responses, it's called logistic regression, because most of the time people use the logit link to describe 0-1 data. So I'm just going to go through and just use the logit link in this example, and we get again a very similar output using the summary function. So you fit your model and you call summary on your data, on your fit, and you get some outputs coming out. Again, the most important part is the actual intercept and the slope. So in this case, it's telling us that the intercept is minus 1.648, and the slope, or grain size, is 5.122. So you can also now use the predict function as well to predict new data points. So predict is used, as I said before, throughout all the models I talk about today. And so what the predict function does is that when you give it your model fit, there's a class attached to that. So for the LM model, it's got an LM class attached to that. For the GLM function, it's got a GLM class attached to that, and that's how the predict function knows what to do. That always mystified me. How does it know what to do? But it's looking behind the scenes to know what model you fitted. And so what we do is we give it some new data. So suppose I'm looking at beaches with 0.4 millimeter grains of sand and 0.87 millimeter grains of sand. Again, it's the same format the predict function expects in the data frame. Now I'm going to tell it that I wanted to output response. So I'm just telling you, for GLM, there's many different, you can get different outputs for your predict, but if you want to get the response, so the probability of it being class 1, you're going to put the response there. So here, if I've got a grain of sand of size 0.4 millimeters, the probability that it's in class 1, or the probability that there's a spider there, is 59%, or 60%, round it up. And if you've got 0.87 millimeter grains of sand, there's a 94% chance it's going to be a spider there. So the thing I like about GLM is it's really nice to see the actual probability associated. It's not just going to be 0 and 1. You can have, there is some nuances. Obviously a 0.4 millimeter grain of sand gets a different response than the 87 millimeter grain of sand. If you round them, so if you say, look, less than 50% chance, there's probably not a spider there. Above 50% chance, we're going to round it up to a yes. They both go up. They both get rounded up to 1. So if you were to try and predict the class, you'd say, look, they're both above 50%. We're going to predict them both as class 1. So that's one way you can do it. You can set up your own thresholds as you want. You can be a bit more strict. You can be more lenient. So what you can do is really nice. You can just say, yes, there's probably both. But if you have to predict 0 or 1, because that's the output in your model, your data is a 0 1 output. If you wanted to actually get the 0 1 output, you just use round. But I like having the information here saying we're a bit more confident with this 87 millimeter grain of sand than this 0.4 millimeter grain of sand as well. And so, of course, probability is close to 0.5, but hard to classify. And that's just one part and parcel of doing machine learning, is that sometimes you're not going to get perfect signal either way. So if it's for example, that one around 60%, it will probably say it's going to be spiders present, but there is a chance that spiders might be present. So obviously you like to have models that have really strong signal, but sometimes it's just not the case. So that's all I want to show you a quick warning. When you are using GLMs, I do love them, especially logistic regression. You have to be careful about a few things. So suppose the scientists who collected data thought their study would look more convincing if the data was perfectly separated. Okay, so they thought, I want to get published, publication, that's all that matters in academia. Got to get it through. Let's just fudge the data a bit. No one was there. And make it very clear that, it's not very clear from my diagram, but they are perfectly separated. There's no overlap between the grains of sand that had spiders and the ones that didn't. And sneaking one for data, how would their GLM look? So if you're trying to be sneaky, it's not gonna be good, okay? So you try and fit your data. So you do the same working out as you did before. So you tell the data set is now data.new, the one I modified. Again, it's spiders against grain size, and we're going to use the same logistic link we did before. Warnings appear, and you just try and ignore those. You just don't worry, okay? I don't know what it's doing. And we look at the summary. Have a look at it. So a lot of people sometimes ignore warnings and don't look at the output. So look at the output. What happens is that your coefficients for your model start becoming really, really big, and they blow up. And so the estimate for our intercept is now minus 112.4. And the estimate for the grain size is actually quite big as well. Remembering the ones we had before, quite big. And the standard error, or the variability associated with these estimates, is quite big. It's a very big number. And so logistic regression doesn't work well at all when you have perfectly separated data. It's due to the mathematics of working with the likelihood if you do statistics. And so if you have perfectly separated data, you just can't use straight logistic regression. There is ways you can get around this. It's called, if you want to do some more research, you can do regularization. So it's a mathematical way we can fix this. or you use something else to model this data. So when you get a warning in R, don't ignore it. So I showed this to my students. They sometimes leave their projects to the last minute, I've been finding recently in semester. But always look at the warnings, and I was talking to a friend of mine who works at an insurance company, and they said a lot of the time you have to be able to know when a model is able to be used and when it's not, and a lot of people sometimes surprisingly don't know when it's actually appropriate to use a model or not. So if it's because you can use something, doesn't mean you should use something in some cases. So I didn't even realize this was an issue. I think I got taught it in second year or third year. I just ignored it, and I didn't realize it's an issue until quite recently. And when I'm working today on a logistic regression type model, and it's not working. So I have a feeling it might be due to some perfect separation as well. So it does come back to haunt you later on. So I'm going to very quickly touch on multiple regression. So multiple regression is a whole subject on its own sometimes in stats courses, but I'm very quickly show you a basic example. So before we had just one predictor against the response, but of course you can have more than one predictor against the response. That's what we have most of the time. We have lots of different information to help us predict an output. So here we consider the data set exam. We have 2 exam scores are given for each student, and the label represents whether they passed or failed the course. So for example, the first student got 34 for their first exam, 78 for their second exam, but unfortunately didn't pass the course. And then, for example, the 4th student here got 60 for their first exam, 86 for their second exam, and they passed the course. So we'd like to know the relationship between exam 1 and exam 2 and whether they passed or not. So if I look at this data here, I can plot it, and I can plot exam 1 against exam 2, and then colour these points by whether they passed or failed. And so we might think here that there might be some sort of straight line that can separate out these 2 classes. So again, we're using a GLM in R because the output itself is pass-fail, which is a 0-1 response. So the inputs again are continuous, so we've got continuous exam scores, and then the output itself is what we're interested in, which is 0-1. And so again, with the GLM function, we have data equals data, this constant thing. And here we're introducing a new terminology. So before, I just had the response tilde predictor, and what you can do is you can specify in R what predictors you want R to actually look at. If you've got more than one, you don't necessarily want to use all of them. But if you do want to use all of them, if you just, instead of having to, imagine you had a really big data set, you want to be writing out every single variable. If you just write tilde dot, R knows to look at every single predictor in your data set. So in this case, R is going to be looking at information from both exam 1 and exam 2. So you have to write out exam 1 and exam 2. And just to be consistent, I'm going to use a logistic function again, so logistic regression. Okay. If I look at the summary of our fits, it's very similar now, but I also get a coefficient. Instead of having intercept and just one slope, when you add more coefficients, you go into like high dimensional space. So now I have a coefficient as well for the second predictor. So you can think of this now as like a plane. And then when you go into like 4 dimensions, you can't really think of it. I wish I could, but you can't. But what's really cool is what we can do is we can plot a decision boundary. And so even though the logistic link is quite ugly and we don't need to want to know about those maths, what you can do is if you look at, I'm going to go back. I should have put a hyperlink. So at the point, so most of the time, the threshold for classifying a point into a 0 or 1 is the 50% threshold. And at that point there, at the 50% threshold, our link is at the coefficient, like the coefficient space, beta 0 plus beta 1x, or if you have more things, doesn't matter how many things you have, that value is at 0. So exactly at 0, you're at a 50% chance you're on the borderline. So we're going to use our fact to help us just describe a linear relationship between whether we're going to predict something as class 1 or class 2 or class 0. Go back. And so when you just rearrange some things, if you look at the logistic function, I'm not going to go, it's not a maths lesson, but you can show that you will predict something as class 1 if your exam 2 score is greater than or equal to minus beta naught, the intercept, over the exam 2 slope, plus minus beta 1, so that's your exam 1 slope, over your exam 2 slope, times the score for exam 1. So you don't even have to know, use the actual logistic, like, remember that logistic link, you can just mathematically, don't worry about the details right now. You can rearrange things and just using your 2 scores and the slopes you figured out, just from that to figure out if you're going to pass or fail. And so here, this can be described as a line here. So any points in this other line, this inequality, get classed as passed. You did well, pretty much well on both exams. And if you're on this other line, you didn't do so well on both exams, so you failed. And so what we've done cheekily is that the nice thing about this logistic regression is called regression because you are regressing. The thing you are predicting is a continuous response. It's the actual probability between 0 and 1, so it's called regression for that reason. And when we round those probabilities, that turns to classification. So you can perform classification within the logistic regression, but people get very sensitive if you try and sometimes put it as a classification algorithm. But it is technically a regression algorithm, but you can use the classification algorithm, which we just saw. So here, we use regression to classify whether we passed or failed. But we're going to go purely into classifications now. I love this meme. I think the original meme just had the dogs and the biscuits, and then people started eating Tide Pods. I think it would be topical to put that in as well. And so we've shown you one classification algorithm, or regression. You can be used for classification, but of course we can't use logistic regression all the time. So I'm going to show you another data set. So we're going to consider the data set microchips that contains test scores, test 1 and test 2, and the label whether or not this microchip passed the test. So maybe some sort of stress test for this microchip. Here we've got test 1 scores and test 2 scores, and then these ones all passed. They're all good microchips. Now, if you quickly look at this data set, we can't use a GLM to predict a class for a new data point because there's no way I can use a linear relationship between my predictors to draw some sort of straight line between test 1 and test 2 to separate out the classes. So this is, you can quickly see here, that's why I always say to plot your data. So if you were to go ahead and try to use logistic regression, you can, but you get garbage responses. And so if you quickly plot your data, you would see here that it seems to be that the ones that pass form inside a radius, inside like a general radius of the bad ones on the outside. And so the reason why it's called GLMs is because it's called the linear component comes to the part that you need a linear combination of your predictors to look at your response. And here is definitely not some sort of linear relationship between the two of them. So the cool thing about machine learning, which I really love, so some people are asking, oh, when is it going to be like the be-all and end-all of machine learning? Like what's going to be like the master algorithm? And the thing I love about it is I don't think there ever will be, because different data sets require different models to describe them. And so while we can use logistic regression to classify data points, this isn't feasible when we have high class separation in our data. That's the spider example we saw before. So if you had that cheeky spider example where you separate out your 2 classes, logistic regression doesn't work there. And also doesn't really work when you have a nonlinear combination of predictors. So what other options do we have? Quite a lot of other options. And what I'm going to use for this data set, someone's commenting on the talk.
Maybe someone's downstairs wanting to get up. Let me see.
Holidays. Okay. So, one of such algorithms is called the k-nearest neighbors algorithm. And the k-nearest neighbors algorithm is awesome. It's because it doesn't assume any particular anything about your data in particular. So that's what non-parametric means. Doesn't assume any of your data follows any particular shape. And what KNN does, I got this really nice graphic from Natasha Latisheva. Sorry if I'm pronouncing the name wrong. Got it online. What it does is if you've got some data points here, you can use it. This has got 3 classes, for example, not just 2. Here you've got some data points here that form class 1, 2, and 3. And suppose you've got a new data point in there. You want to say which class does it most likely belong to. So what you do is that you calculate the distance between your point and all the other points. You then sort them out into which points are its nearest neighbours, so which points are the closest. And depending on how many neighbours you consider, that's why it's called K nearest neighbours. You might want to consider the first neighbour, the first 2 neighbours, and so on. You choose your class depending on the vote of the nearest neighbours. So in this case, this is 4 nearest neighbours. And in this case, for the first 4, 2 of them voted class 1, 1 of them voted class 2, 1 of them voted class 3. So the most majority one was yellow one. So you would predict this point here as a yellow class. So how do we actually do KNN in R? I'm just going to show you through the example of that microchip data set. So what I'm going to do is I'm going to separate my data out into the predictors and the response. So I'm going to call, a lot of convention all the time in statistics and machine learning is to call your data, the predictors, X. And what you can do is you can also call your class labels just class. You can call it, I just called it CL. And so if I look at my data set beforehand, my data laid in the first 2 columns and the class laid in the last column. So here we have, I'm going to subset the first 2 columns of my data, and then just think, you want to make sure that your class is as a factor and not as numeric, so R can interpret that as a class rather than to predict it as like a 0, 1 value. Now for KNN, so the algorithm I showed you before, you trained your data, then you use a predict function to go in and predict a new data point. But for KNN, it fits and predicts at the same time. So you've got to actually get the new data points at the same time as you fit the algorithm. And so there's no right or wrong way to do it. I'm just going to show you like an extreme example of what you can predict. So what I'm going to do is I'm going to consider, imagine my data was all in here, I'm going to try and predict the whole grid. So if I've got a whole grid in that set, how would the KNN algorithm predict on either side? So this corresponds to this pretty much. Imagine these grid points are in the background of this data set here. And the way I did this was just using the mass package. So there's many different packages in R. Mass is a very useful one when you're looking at classification and just working with normal distributions. But mass, there's so many cool things in different packages everywhere that I would have guessed if I never tried. I didn't even know this existed until the other day. So it's a really cool thing where the expand grid function just gives you a set of data points that fill a grid. You tell it the endpoints for that grid. This workshop's not too focused on the R code. So what will be useful is if you want to know more about it, is to you can run this code at home as well and see how the graphics work out as well. Now the KNN is not an inbuilt function into R, so LM, GLM are inbuilt into like the base R. However, KNN function lies within the class library, so you have to call that library first. And I'm just going to call my classification classif. Everything's always like an abbreviation with me. And so what you do is you feed it in your data set, so the original data that you had. You feed it in your new data points. So new data points was the whole grid of every single point I could imagine on that data set. You feed it CL, class was your labels. And what it's going to do is I decided to use K equals 3 neighbours. So I'm going to look at the votes of the 3 nearest neighbours for all those points. And then prob equals true. You don't have to use this. You don't have to use prob equals true, but this helps me plot something on a little bit later on. So what this is doing is for every single new data point I put in, the KNN algorithm is looking at the 3 nearest neighbors of those data points and then voting on what it thinks that data point should be. So you have to have it in the form of the training, what we call it is the data you're inputting, what you want to be predicted, your new data, the known classes of your data, and how many neighbors you want. And so the R code to generate this plot is not very nice. So this is not a ggplot tutorial, so I thought it's in the slide RMDs. If you want to have a look at it, it's all in there. It uses a dplyr package, so it's all tidy. So what we can see here, I'm going to describe what it does. And so here is the original data points I had, but in a slightly different look. Here is that grid I had before. And using the KNN, using the 3 nearest neighbors, I just colored the points on what the algorithm thinks they should be. And so it works pretty well that everything inside this ring gets put as class, that was the passing class, and then everything on the outside is the failing class. So it's doing a really good job at picking up the separation between like the circular notation, because it doesn't assume any shape of the data. It's just using the 3 nearest neighbors to decide what class it should be. And the reason why I did that prop equals true, you can actually get information about how much they disagreed on a class. So if you got a really high probability, that means that they all agreed. Here they all said its point is class, that failed. But here, when you've got smaller points, this is saying that it failed, but we're not quite as sure. So there was some disagreement there, probably due to this point here, adding some disagreement to these points here. I can change how many neighbors I consider. So you might want to consider the 9 nearest neighbors. So there's no right or wrong with KNN. A lot of the time it's trial and error to figure out what number of neighbors works best for your data set. So if I pick 9, you get a slightly different output, especially around the points that are close to the boundary as well. So here we only consider 3 nearest neighbors. All these points here are very strongly coded as failures, but when I consider 9 nearest neighbors, some of these points here got considered as passes. I like to use an odd number of neighbors. That avoids having ties in your data set, so you either have to have a majority, you kind of tying between 3 people. So if you want to avoid ties, I will do it for you, but if you're doing things by hand, avoiding ties, you can also use just an odd number of neighbors to avoid the situation as well. So what other classifiers exist besides k nearest neighbors? So this is a meme I saw. Here, in this case, we have a k nearest neighbors. If you were looking at 3 neighbors, you'd be classified as a red. If you're looking at 5 neighbors, you'd be classified as a blue. Just lol. Another one of my favorite ones is decision trees. And decision trees determine predicted values based on a series of questions and conditions. So I saw this really funny example online by Igor, which is we always use decision trees in our mind implicitly every day. Am I hungry? Yes. Do I have $25? Yes. Go to a restaurant. Oh no, buy a hamburger. If you're not hungry, don't eat, just go to sleep. And so when we make decision trees in R, there are many things to consider. How many features in our data set do I consider to put in my tree? Or what is the threshold for classifying into a yes or a no answer? So luckily for us, we're not going to go into answering those questions. R does these magic and figures out what features to use and what's the threshold for you. You can learn about how you can work out trees by hand. That's how I did it in 3rd year stats, was by hand. Not very fun, but R does a lot of stuff for you. And the function that does that for you is ArePart. So it's very cool function, and we're going to be using a very overused data set for this example, which is the RS data set inbuilt into R, but I think it does a pretty good job for the decision tree. And so we have, if you're not familiar with the data set, it's already inbuilt into R. So if you just type in head iris, the data, you'll see the data popping up. And so if I look at the first 6 rows of iris, I see I've got 4 predictors. So I've got sepal length, sepal width, petal length, and petal width. And I got what species of iris it was. And what we're going to ask ourselves is, how can we construct a decision tree to determine the species of iris? So RPart lies in the RPart package. So a lot of packages are needed to do a lot of machine learning. And as we see again, it's a very similar type of argument that goes into our functions. So here I'm going to call it tree because it's a tree. And the first thing I put in is what I want to predict and what I want to use to predict it. So in this case, the response is your species. So there are 3. I'm not sure how many kinds of species. Three kinds of flowers. And we're going to use all 4, as far as you've used 4 predictors. We're going to use sepal width, sepal length, petal width, and petal length to help us decide what flower it is. We're telling it it's the data equals iris, it's the iris data set. And the method we're using is class. So we're telling it to classify points because you can do regression as well, decision trees. So we're going to use it today for classification. Another fun library, you don't have to plot your decision tree if you don't want to, but I think it's really cool to plot the actual tree itself. And a nice library that does that for you is the ArePartPlot library, and the actual command is also the same name as the library itself, so it's ArePartPlot. So once you've fitted your tree, you put that fitted model into ArePartPlot, and you can visualize the tree. So what do we have here? What it's saying is that the R in the background has done some working out to say that the first level is for the petal length. If your petal length is less than 2.5, yes, you're a setosa. So all you need is one question to determine whether, if it's yes, you're a setosa, no more questions to ask. If it was no, so if your petal length was greater than 2.5, we then look at the petal width. And so if your petal width was less than 1.8, you're a versicolor, and if you're greater than 1.8, you go to a virginica. So it's a very basic tree. And you can see here that we've only actually we told R to use all our predictors, but only 2 of them were needed to separate between the 3 flowers. So petal width and petal length. What you get from the information from the nodes itself, it shows the class you predicted, so setosa, versicolor, and virginica, and percentage of observations in each node. So 33% from my data set were setosa, 36 were versicolor, and 31% were virginica. So if you got a new flower, you're avid plant person, and you measured your flower, and you want to know what species it was, you would feed in the information about the flower. And so here we would say, suppose I just picked it out at random. Sepal length equals 5, sepal width is 3.9, petal length is 1.4, and petal width is 0.3. What you could do is go to the tree itself, and you've got it right there, and figure out what the flower is. And so here the first decision is petal length less than 2.5. Yes, it's less than 2.5, so it's going to be a setosa. And so that's what we see. When we actually do predict with our tree and our new data, we get the setosa coming out. So what you can do is you can use a predict function. That's probably the normal way to do it. But if you want to have some fun, you could actually do it by hand as well, because the rule is right there in front of you. You got a very simple data set. So I think it's quite nice that there's a decision trees. All you need to know is information about one particular variable, and automatically you've classified your point. Now, a single tree is prone to overfitting. So what is overfitting? Overfitting is when you match the data you give it in too well, and then when a new data point comes along that's slightly different, because you match the features of your own data set so well, it doesn't really handle a new point that will. And so this is what knowledge, experience, and when you overfit, you try and see something that's not really there as a cap. So what I'm going to try is I'm trying to walk through what we call ensemble learning very briefly. And I'm going to walk through, there's a lot of me talking, not enough words on the slide. So what we can do is we can use this concept called ensemble learning. So what ensemble learning does is that it uses a combination of what we call weak learners, and we put all the information in of these weak learners together to get a better response coming out. So we're using, I think it was a hive mind. So how do we actually do this? So what we do is we have our data set. Here's all our data. And what we do is we're going to sample with replacement. So with replacement means that once you take a point out, you can put it back in and observe it again. What we're going to do is we're going to train many different trees for subset of this data. So this learner, in this case, corresponds to the tree because you can use ensemble learners for different types of machine learning methods. So in this case, learner 1 corresponds to a particular tree, but you're only using a subset of the data for this tree. So you're not using all the data, you're using a subset. And again, you repeat this with learner 2, and you can do this up like how many times you want. You can do 50 times, a million, obviously not a million, we don't have all day for that. But you just repeat this process quite a many number of times. We train all these trees with this small subset of, not small, but a subset of the data. And they all have their own models. So one tree's been given some data, so it makes its own model. Another tree's been given another one, so it's got its own model. And then when you feed it a new data point, so suppose you give it a new data point, so maybe another flower, measurements for example, this tree will classify it as some class. This tree will classify it as some class. This will give your class out. And then what you do is you take the majority vote of what class it all thinks. This is what ensemble learning is. So you just have, instead of having one grand master tree, you then give many different trees a smaller subset of data, train them all, and when you got a new data point, you just take like the average, or if you're doing, you can do regression with trees. So if you're doing regression, you take the average output of those trees. If you're doing classification, you take the mode, the most common response as your class. And this is called bagging. It stands for, I used to think it was bags, you're putting the data into bags, that's not what it means at all. It stands for bootstrap aggregating. So the bootstrap comes from the fact that you're taking multiple samples. If you do statistics, and aggregating means that you're using all the information at the end to come up with some informed response. Now, there's not really a bagging function in R. What we see in R is called random forest. So some people might have heard of random forest before. The only difference between random forest and bagging is that instead of taking only a subset of the data, you take a subset of your variables as well. The reason why you might do this is because of tree correlation. So if you were to use all the variables every single time, if one or a few of those features were very strong predictors for the response variable, then these features will be selected many of the trees, causing them to become correlated, and this can reduce the accuracy of the ensemble. So you really want things to be quite different between all the trees, and they have different responses. Like, the reason why you're doing ensemble learning is to really prevent overfitting. And what you're doing is you're trying to give it different scenarios of what could happen with the data. And so if you have high correlation and it's not doing a very good job, this reduces the accuracy of the ensemble. So all random forest is that you give it a subset of data for each tree, and you give it a subset of your predictors as well. So for example, for the RS data set, some trees might only get 3 out of 4 of the predictors each time. You don't get all of the information at once. But it's the same process again, where each of those trees, if you give a new data point, they will all tell you what they think, and you take the mode as your classification. So we can do random forest very easily in R. So I'm going to use the same RS dataset to show you that the random forest will also give me the same response as the ArePart function. But it's because it's a very basic data set, there's not much difference between the two of them. So with random forest, that lies in the random forest library. And one thing I always made the mistake of was forgetting to capitalize the F. And be like, can't find the library. I'm like, oh, it's random forest. So I'm going to call my model iris.rf, so iris.randomforest. So in this case, I have it's really nice. All of the functions match their package names. Very easy to remember. So it's random forest. Again, it's a very similar notation. So it's species. We're going to do tilde dot, so we want to use all the information, all the predictors, and we're using the iris data set, so the data set is iris. If you just write iris.rf, you get some information coming out. So it's telling you that there's a lot of, with random forest, there's a lot of things you can change. It's a lot of tuning parameters. You can tell it how many trees you want to consider. You can tell it how many predictors you want to consider. But the default random forest works pretty well most of the time. So it's doing, if you don't specify things, what it's going to do is it's going to do 500 trees by default. So what it's doing is, in the case we had before, we have 500 of these learners all going at once, and they're all giving us, they're all voting on what they think the class should be. And an output that will come out is called, we're going to be going into a bit more of this next time about how we actually assess model performance. But the thing that comes out is called the confusion matrix, so I think it's really interesting. So the confusion matrix tells you how the algorithm might have got confused along the way. So what we see here, it tells you what the true class should be and how it predicted it. So in this case, we predicted all of the setosas perfectly. For the versicolors, we predicted 47 of them as versicolor and 3 of them incorrectly as virginica, and then the same relationship the other way around. So for virginica, 47 of them were predicted correctly, but the 3 of them weren't predicted correctly for the virginica as versicolor. But we'll look at that in more detail in the assessing model performance next time.
I didn't know it's not the other way around, where 3 were correct and 47 were incorrect.
Oh, I think you go, you read along, it goes the other way around, so it was like 3.
You know, you said 47 were correct, 3 were incorrect.
Yeah.
But how do you know it's not the other way around? It's,
The errors.
yeah, the error is the other way.
Well, in this case, it has to kind of add up. So if we see here that you either read along the rows consistently or you read along the columns consistently. So in this case, the on diagonal element corresponds to how many was correct for versicolor and versicolor, and so anything that's not on the on diagonal corresponds to the case where you got it wrong, and then what class you got it wrong to. So you want the higher the diagonal is, the better, and the bigger you get off the diagonal means your thing wasn't working very well. And again, the predict function comes in play, and it's always the same format where you put in first the model you fitted, and then the new data you put in. And so this is the same data I used for the RPart function. And so if I give the new data, which was I made up on the spot, sepal length equals 5, sepal width equals 3.9, petal length equals 1.4, and petal width equals 0.3, it also tells me that it's a setosa, just like the RPart function also said. The nice thing about the RPart function is if you have a very simple data set that's not too crazy, the RPart function allows you to see the actual tree that it's modeling. But a random forest, it's really hard to visualize these trees because you've got 500 of them. And so you actually don't know how the inputs match to the responses. All you know is that you put in some data, made 500 trees, and then the average, like the mode or the majority response was setosa. So my ethos of machine learning is if you can fit something simply, you should fit something simply, because a lot of times it's a lot easier to interpret. we saw before, we knew how these two variables, the petal length and the petal width, corresponded to what class you go into. But random forests really have no idea what it's thinking about how it's classifying these points. So sometimes random forest is called a black box algorithm because you really don't know how it's making these decisions because it's got 500 of these trees. They don't all have the same predictors. They don't all have the same data input, and it's hard to say how each changing a predictor changes the output. So I've shown you random forest and I've shown you RPart. And so RPart's really good for very simple, small data sets, but I'm going to show you a bigger one. So I said before that I work with gene expression data. We're going to look at some gene expression data here. I'm not actually, it's too big to actually visualize, but we can get a general sense of the shape of it. So this data set has a response variable Vy. This is sometimes if you do a PhD, you inherit the labeling conventions of your supervisor. So my supervisor, if it's a vector, he calls it V, and in general in statistics, if it's a response, it's called Y, so it's Vy, which is a factor of 4 different cancer subtypes, which is called, don't worry about what cancers they are, I don't care about what cancers they are. It's by the point the data's got to me, all the biological stuff has been done with, and all I care about is classifying them. I don't actually know too much about the actual biology behind this data set. So we have 4 different cancer subtypes, and the gene expression comes from 1,586 genes and 63 observations. So I have 63 people in this data set. They all have, I've trimmed it down to 1,586 genes for each person, and each person will have one of these cancer subtypes. And so in this case, my data I should have put up here, the data is, like the predictors are called MX, so M for matrix, big X for X. So it's pervaded all throughout my coding now. So here, this data comes from my package, small promotion called multi-DA. It's because it's an introductory workshop, I'm not going to go into how this method works because no one will need it. Unless you're working with gene expression data. But the data set's up there on GitHub, so just thought I'd say that if you want to actually find the data set and work with it as well. So you can, on my GitHub page for the slides, you can see how you can, the package is only on GitHub, it's not on Crown just yet. So you would install a package from GitHub, and then you would call the multi-DA package. And we can have a look at, and the data set is called SRBCT, because it stands for small, round, blue, circle tumors or something. And so here we have the 4 classes, and we have 8 that belong to class 1, 20 that belong to class 2, 12 that belong to class 3, and 20 that belong to class 4. And just a sanity check, I have 63 rows in my data and 1,586 response predictors. So it's like this is what we call high-dimensional data, where I have a lot more features in my predictors in my data set than I have observations. And so if you go into statistics, these are not fun to work with when you've got more things that you have to, like information, than the actual observations itself. And so just keep in mind, I had 1,586 variables. If I do a simple decision tree, what I do is now I'm going to show you a different type. There's many different ways you can input the same information into R functions to get the same result. And so you'll see here in this line of code, it actually omitted what data set it comes from, because if you actually input the information itself, so here I'm actually directly putting in the Y vector, and here I'm actually directly inputting the data frame itself. If you actually put that in itself, you don't have to worry about specifying the data set where it comes from. So I'm just showing you different ways you can do the same thing in R. So here I've got, again, the response against all my predictors. That was it's a data frame of 1,586 observations. So I know it's called MX, but it's only because in the maths it was a matrix, but in R it's a data frame. So I fit my tree And if I plot my tree, you can see here that out of the 1,506 variables, I've only used 3 of them. And so what this is saying, this data set is not very, it's not named very well. So this just says that gene 708, if that's greater than equal to 0.013, you are class 2. If no, we look at the 108th gene. If it's less than minus 0.46, so that's no. It goes to class 4. Then we have one more decision to make. If you were yes for this condition, we look at now gene 153. If you're less than minus 0.53, yes, you go to class 1, and then no, you go to class 3. And so decision trees can sometimes be overly simplistic. So we obviously don't expect every gene to have to affect what cancer class you're in, but intuitively you might think that more than 3 of them contribute. Cancer is a very complex beast. And so in this case, we're going to show you next time that this method doesn't actually work very well in predicting new data points. So I'm not going to show you that today because how we actually look at model assessment is a whole different topic. But spoiler alert, when we try and fit new data points to this, it's not doing too well in predicting new data points. So I'm going to show you how you might fit a random forest. So we can also, because I've got such a big complicated data set, maybe you might want to avoid overfitting. I might want to try a random forest. So in this case, another type of input into R. So if you're doing random forests and you're inputting, you're not using a formula, you're just inputting the data as it is, it actually expects the other way around. So it actually expects data first and then response second. So in this case, I put in my predictors, that big matrix, 63 observations, 1,586 genes or variables, and then here were the classes of the cancer subtype. 63 of those all together. So if you get something to get an error, it's because your things aren't matching up. You need to have one response for every row in your data set as well. And if I have a look at the print statement from there, by default, again, it uses 500 trees. For each split, it is trying 39 different variables at each split. And for this particular data set, we have a 0% error rate for our own data set. So if you try and fit your data for this particular data set, we see we're doing pretty well. We're actually classifying all class 1 correctly, all class 2 correctly, and so on. So it's doing, although you can't really, we're going to show you next time that these things can be quite misleading. We need to see how it's working for the whole data set. So one thing to note is that R can be sometimes very inconsistent with the way, if you change different formulations, sometimes ordering changes. So here now, X is first, Y is second. And so I always like to look at the documentation for the functions if I'm going to change things up. A lot of times the errors will guide you as to which things you need to fix. So when I was running this, I first had Y first and then X second. Then it yelled at me. So then I switched it around. And I thought I'd just have a bit of a warning because I had made this mistake myself. And so for the paper that accompanied this package, I had to compare my machine learning method to other methods, and the one I compared it was, one of the ones I compared it to was random forest. And so I was actually comparing against random forest, and I saw that random forest was doing really bad. I'm like, yes, random forest is doing so bad. That's because I can put in my data incorrectly, so it was actually my fault, not random forest's fault. And so when you're using random forests, or actually many of the classification methods, because both of them, many methods can do classification and regression, the type of data you put into the machine learning method, it will use that to determine what it's going to do. So if I had accidentally, remembering that my class was a factor, 1, 2, 3, 4, and that was a factor type in R. So that's, R knows that that factor means like categorical data. And the 1, 2, 3, 4 is a placeholder for those categories. If I'd actually put in a numeric vector, 1, 2, 3, 4, whereas R is thinking, these are numbers. If you put in a numeric Y, what random forest does is regression. So it's actually trying to fit a number like somewhere between 1 to 4. And then that doesn't work very well, okay? So then you get, it's not as much information coming out from the regression, but if you were to try and do your model assessment, it's not going to be very good at all because it's not predicting what you want it to predict. So you want to be able, if you give it a numeric type, it will do regression. It will try and predict some continuous number, but if you put in a factor, it will do what you want it to do into classification. So what I had done when I was doing my method, I had put in numeric, and that's why I thought it was doing badly. Then I realized very quickly that I was just doing something wrong. But this also applies to many other machine learning methods as well. You don't ever specify, sometimes you don't specify directly classification or regression. It will infer that automatically, so be very careful about what is inferring. So I realize it's only 8 o'clock, so I've gone a bit ahead of time. But there are many more machine learning algorithms that I haven't touched on today. And this list here isn't even exhaustive. There are many different types of algorithms out there. But some of the more popular ones are support vectors machines. And you can find a really good package for this in E1071. So it's not a very, some of the packages are nicely named, some of them are not. So I think this package is called this because it came from a lab that was called E1071. There are many different types of tree models. So random forest is just one different type of tree model. But another tree model is called extreme gradient boosting, where in boosting, to give you a quick summary of what boosting does, is that boosting looks at, for each alert, so it's also another ensemble algorithm where you have many different trees, but what it does is it learns from the stakes of the previous tree. So if you, for the first tree, give yourself to the data, it then trains the tree, and then it tries to repredict based on that tree, and it looks at how poorly predicted the data points. And then what it does is for the next tree, it gives those poorly predicted points more weight. So they might be P again in the next tree. I guess it gets better and better at predicting the data points. So that's what gradient boosting does. But there's more things to tune for that. So that's why I don't like this. Gradient boosting is one of the ones that's used a lot to win cattle competitions these days. And they do really well. With a lot of tuning parameters associated with boosting trees. There's also discriminant analysis type methods. So these are classification methods. And these are you can find these in the mass package, the sparser scrib, my package, and the PAMR package. And these look at seeing how you can pretty much separate your data into normal distributions and then use that to classify your data points. I touched on before that logistic regression can't be used when you have perfect separation. What you can do is you can use regularized regression in this case. It's called regularized GLMs. I hope I never have to teach this because I would always stuff up that word. That's found in the GLM net package. And also the big hype these days is neural networks. They're another one touched upon. And you can find neural networks in the neural net package and also in Keras, which is also used in Python as well. So Keras is a package that does neural networks, and I think it calls on something called TensorFlow to do all the hard mathematics behind it, because neural networks are essentially a very big calculus problem. And so it needs a lot of back-end support to be able to calculate these things. For neural networks, I kind of thought that they could maybe future, someone else wants to, if anyone's an expert in neural networks, I'm not an expert, but I think there's something that need a whole talk on their own because they're a big beast. But if you really want to know about neural networks, I saw a really good video by someone called 3 Blue 1 Brown on YouTube. He's the most brilliant person on YouTube I've seen. I think any mathematical concept he can describe to you, he changed the way I saw linear algebra. If you ever struggled with linear algebra, he's got a very good 3-part series on how neural networks work from a mathematical perspective, and there are some really good tutorials online or how you can actually use them. But because there's so much involved in half of the work with neural networks is looking how they perform, do model accuracy, I feel like I can't really talk about them until we actually know how to actually see how they see how well models perform. But to give you a very short rundown on how neural networks work, it's pretty much like repeated logistic regression or linear regression over and over again. So it's if you go online and watch 3 Blue 1 Brown videos, it won't seem as scary anymore. You won't be as impressed when people work with neural networks. And one bad thing about neural networks is that it's like random forests, where it's not very obvious to see how changes in your predictors match to your outputs. So one thing it's only got a few slides left, is that when you're doing machine learning algorithms as well, you got to ask yourself, what is your goal of doing machine learning? Are you trying to learn stuff about your data set? Do you want to know how your features map to your response? So, for example, if you're a student studying for exams, you might really want to know how your scores in exam 1 and exam 2 are affect if you pass or not. Okay, this might be useful information to have. And so you want a really intuitive algorithm to know whether obviously, I think we can see from this diagram that the better you do in both exams, the more likely you are to pass. But sometimes you don't care about how you got to the prediction, you just care about having the right prediction. And so that might be, for example, Amazon on Facebook ads. They just want to get the right prediction for the right ads for you. They don't care about what features go into it. They just want you to see the right ad most of the time. You're going to be clicking on that ad. But for example, be a doctor who's working on gene expression data, you might want to know what genes cause cancer so you can actually do something about it. So it might be like to a patient, look, you're going to die. We can't do anything about it. But you want to be able to, use that information to do something and change the world. And so what we call in statistics is all about prediction versus inference. So sometimes you've got to trade off between interpretability and prediction at some points, depending on what your interests are in machine learning. Obviously, you want to get a balance of both. So too simple models don't sometimes predict as well, but too complicated models aren't as interpretable. And that's it. That's thank you. So that's part 1. So if you have any questions about these algorithms, you can feel free to ask me. And I just want to say thank you to Emmy, who's in the audience. These slides not being possible without her kunoichi. Is that how you pronounce it, Emmy? Kunoichi theme slides. And then Yihui, who developed Jarangan to begin with. So it was actually incredibly easy to use the split design thanks to Emmy. Mark Greenaway helped host my Shiny app that I showed before. Last time I used Shiny apps or IO, I ran out of hours. So Mark helped me put on another server. And also the RLadies Sydney team for actually organising this and for everyone to come here. And then next week we'll be assessing model performance. And so the comic I have here is that the robotic uprising used spears and rocks and missiles and lasers. And that's because they looked at the majority of battles won in history, and most of them used pre-modern weaponry. And so thanks to machine learning algorithms, the robot apocalypse was short-lived because they learned the wrong things to do. So, so yeah, we're going to be looking at next week how to assess model performance. So if you want a bit of a sneak peek, essentially what we're going to be doing is first touch on concepts of performance for regression. So this will be covering things such as the mean squared error. And then for classification and regression type algorithms as well, what we're going to ask ourselves is how can we build an algorithm or a code where we resample from our data set and see how well it can predict new data points given a subset of our data. And what we're going to do is we're going to build our own loop together, and then I'm going to show you a shortcut you can use afterwards. So there's a package called the carrot package that does this all for you if you have a model that they know of. But for example, my model I built myself is not on carrot yet, so I have to build my own it's called cross-validation algorithm. So it's good to know how to actually do it yourself so you actually understand what carrot is doing in their algorithms as well. So that's next week. And
Amazing.
thank you.
Awesome. I don't know about you, but I am just wishing that Sarah was my research methods teacher way back then, right? Like, how have I gone so far not really understanding the nuts and bolts? Anyway, I think we have time for a couple of questions. If anybody has questions that they want to throw at Sarah. Yeah,
Oh,
the
it's,
YouTubers.
I'll show you. 3 blue, 1 brown. And so here's like theories about quaternions, whatever they are. But they do have here you see the ones some that I played, which is what is a neural network. Very trendily recently has been the Riemann hypothesis. So if you want to know about what that is, mathematics, he's got something there. He's also got a really cool video about Bitcoin as well if you want to know how Bitcoin actually works. But he's got a 3-part neural network series. It's one of the most amazing things I've watched on YouTube.
Nice.
Yep.
Yeah.
So, if you don't have enough data about the response, how do you go about solving that problem?
It's hard. So the one what statistics will tell you is to get more data. But sometimes if you've got a small amount of data, you have to take what you train with a grain of salt. So unless you can, and then also reducing model complexity. The more parameters you have to fit with such a small amount of data, that works really poorly. So if you can have a simple model that describes these things, the less things you have to fit, the better. But it's really hard to work with small sample sizes, and it's like a statistical problem overall rather than anything particular to machine learning. I can only, for example, with the data sets I was working with gene expression data sets. It's very expensive to get gene expression data, well back in the day it was. That's why for that SRBCT data we had only 63 patients and 1,500 genes. I had to develop a method that assumes certain things about the data to be able to make predictions. But I think just overall, unless you have, it's only so much you can do with a small amount of data. There's no quick thing you can do to get better answers, I guess.
So you have more data, but you don't have the response variable as much. So would you?
Are you saying that some of your data is unlabeled and then some?
Yes.
Also, if you have some of your data unlabeled, that's actually. So I said there's 2 main types of algorithms: there's supervised and unsupervised.
Yeah.
There's actually one in the middle called semi-supervised. So semi-supervised, you have some of your data being labeled, and there's a different algorithm you use to be able to get information about those You use the labels from your labeled points to help you infer the unlabeled ones, and then you put it all together to help you infer a new data point. But they're a whole different class. There's a whole different beast altogether. Yeah. They're not as widely used. So I tried, for my first project, I tried using semi-supervised algorithms. And depending on the type of data you have, sometimes adding more data without labels doesn't really get you, sometimes won't get you as far as you think it will.
Is your package specific to gene expression data? Is that why you put it together? What does it do? What does it do?
My package, what it does is, maybe I'll get it up.
Yeah, show us.
It's not applicable to most people because it's a very specific type of data set you have to have. It's not just for, it just happens that the data sets that mostly fit our assumptions are gene expression data sets, but if you have any other type of data that fits the assumptions, then you can go ahead and use it. But what we're assuming is that you have a high amount of variables and a small amount of predictors. So that was the case of that cancer data set I showed you. And what we're assuming is that within each feature, you can separate the classes out into normal curves. So that's the big assumption we're making, that within each feature, you can get, this is going to be embarrassing. I don't think my vignette's the best vignette just yet.
It's a work in progress.
But for example here, this is a particular feature of the SRBCT data set, we can say that we can group the classes together. So we might have class 1 and class 3 together, and class 2 and class 4 together. And we theoretically say that they follow normal curves, and we can use that information to predict a new data point. So we make the strict assumption about normality in my data set. So if you don't have normality, you can't use it. And we're assuming that all the features act independently on the response, and there's no interaction between the features, which is very unrealistic in cancer data sets, but we make that assumption anyway because it makes the maths a lot easier.
Okay, awesome. Any other questions? Yeah.
I noticed you convert everything to two-dimensional plots. Or even the multi-dimensional, you've got two sets of plots, X and Y, for each of those.
But it's particular with this one here.
Yeah, that one there.
Yeah.
But even in the other linear models that you're using, we always have X and Y axes.
Yeah.
Do you ever do anything with 3 dimensions? In the sense of
plotting.
Or plotting, yes.
It's the more dimensions you get, it's harder to plot these things. So I just picked really small data sets to make it visually appealing.
Yeah.
So if you wanted to do, if you had more than like this X and Y, you'd have to start doing pairwise plots. And a lot of times, if you've got lots of variables, it gets a lot more harder to plot them. I just wanted to show very small data sets that we could actually visualize what was going on. And in this case here, we're only looking at one particular feature, and so the feature has a set of values, and this is called, in statistics, it's a density plot, so it's very like a histogram. And so this is 2D because it looks 2D because I have a histogram and it separates out 2 different classes. So a lot of times you can, if you want to visualize things, you can separate into lots of, if you can, separate into many different plots, but you might not always be able to put everything on one single plot if you've got big data sets. Everything here was very simplistic. In the real world, everything's a lot more ugly, unfortunately.
Awesome. Any other questions? Excellent. Thank you. Let's all thank Sarah again. That was amazing. And we can't wait to see you all back here this time next week for take 2. Anyone who wants to help us with the beginner series, totally find me or Lisa or Danny and put your hand up. We would love you to get involved. So we'll see you next week. Thank you.
Thank you.